Today we are going to look at how we graph to solve systems of linear inequalities. So we're going to actually solve some problems. These are all level 4 questions on your rubric. So you want to do the best you can, but ultimately make sure that you are solid with the level 2 and 3 material. So the first example is a company makes 2 types of boats on different assembly lines. They either make aluminum fishing boats and they make fiberglass bow riders. When both assembly lines are running at full capacity, a maximum of 20 boats can be made in a day. The demand for fiberglass boats is greater than the demand for aluminum boats, so the company makes at least 5 more fiberglass boats than aluminum boats each day. So what combinations of boats should the company make each day? So we want to solve for all the different possible combinations that could occur. What we have here is we've got fiberglass boats and aluminum boats. So let's let X be one of them. We can say that X is going to be the number of aluminum fishing boats, and that Y is going to represent the number of our fiberglass boats. All right, so we do need to start with that. The other information that we have to consider is, are we dealing with discrete or continuous data? Well, we're talking about the number of boats, and we can't make half a boat or a quarter of a boat, so we are dealing with discrete data. And the other thing we have to consider is, are we dealing then with whole numbers or with integers? And in this case, it's all whole numbers. You could make 0 of them, but you could not make -1 or -2. So we are confined to all whole numbers. So what that means is that on our grid, or on our Cartesian plane, we are only going to be looking at the upper or the first quadrant of our data. So now we have to look at the information that they told us. They said that a maximum of 20 boats is going to be made each day. So no matter how many aluminum you make, add it to the number of fiberglass, and you cannot be more than 20. You could be 20, so the equal sign does get thrown in there, but you cannot be more. So the total amount of boats made are either less than 20 or it is equal to 20. The other piece of information that they tell you is that the company makes at least 5 more fiberglass boats than aluminum boats. So what we have is the number of fiberglass is at least 5 more than the number of aluminum. So however they make for aluminum, that's your X number. Say they made 1. They have to make 5 more of the fiberglass. So you have to add 5. Or we could make more. So now what we have to do, we have our 2 inequalities. So now we want to graph them, and we want to find our intersecting regions. So if we start with our first one, the X plus Y less than or equal to 20. Now in these cases here, when we are dealing with discrete data, it may or may not be worth putting into slope-intercept form. At this point, because 20 is going to be our largest value, if you want to have a grid that's got a total of 20 in your X and your Y, that is fine. But when you start to get higher than that, you may want to use the intercept method. For now, what we could do is we've got Y less than or equal to -X plus 20. So what we are saying is that our Y-intercept is positive 20, and then we are going down 1 and over 1. Our slope is -1. Because it's discrete data, we want to plot each of these points, and because it was an equal sign, these points are included, so it's not a dashed line. So we're plotting our boundary here. We're going down 1 and over 1 each time, starting up at 20. So we have our first inequality plotted, the boundary of it. Now we need to determine if we would be stippling, and we're stippling because it's discrete, below to the left or above. So what we can do is we can choose to use a test point, and we can use 0. So we substitute it into the original inequality, and then you look. Is 0 less than or equal to 20? And the answer is yes. This is a true statement. So that means 0 is part of the solution. So what we are going to be doing is we are going to be stippling on this side. And I'll leave it like that for now. So now what we do is we take our second inequality, the y greater than or equal to x plus 5. We already have it in the form y-intercept. So what we are going to do is we are going to start up at positive 5. That is our intercept. Our slope is 1 over 1. So we're going up 1 over 1, up 1 over 1, etc. And again, because of the equal sign, we do not put a dashed line. They are just dots on the intersection of the grid, on the whole numbers. So now what we have to do is we have to determine whether we are going to stipple above or below this line. So we can choose our test point, let's say of 0, 0. So we're going to have 0 greater than or equal to 0 plus 5. So 0 is greater than or equal to 5. Is that a true statement? No, 0 is not greater than 5. It's a false statement. So we are not going to be stippling where 0, 0 is. 0, 0 was down here. So we actually have to go in the opposite direction. And as you can see, we now have a very definite overlap. The overlap is in this region here. So we can remove our arrows, and we can stipple this region. Now the question is, when we are stippling, are we going to stipple the points between the intercepts along the y-axis? Are those possible values? And the answer would be yes. These are whole numbers. In this case, the x's are all 0, but 0 is a whole number and it is a possibility. So we do include these points. So we are stippling this region. So now we have all of our possible combinations that would satisfy this solution. So now what we do to determine what combinations of boats the company should make each day, any point with whole number coordinates, so you're making sure you're only choosing whole number coordinates, in the intersecting or overlapping region is an acceptable combination. So for example, X was our aluminum boat, so that's this value down here. Y was our fiberglass. We can choose any of those blue coordinates. So let's say we wanted to pick this one. We would simply find what its coordinates were, and it would mean we would have to have made 2 aluminum, and it's up 1, 2, 3, 4, 5, 6, 7, 8, 9, it's up 10, and so 10 fiberglass boats. That satisfies our inequality. That's only 12 boats, so it's definitely less than or equal to the 20. And 2 aluminum plus 5 is 7. So they're making at least 7 fiberglass. So there definitely is that separation. So any of those combinations in that blue stippled region are acceptable. So really, when you look at this question here, the only new part that we have added to make this a level 4 is the fact that you need to interpret it and come up with the inequalities. And I'm not saying that is easy by any means. That is why this is a level 4. But you have to initially figure out these 2 inequalities. Once you have the 2 inequalities, The process is the same as what you need to do to be a level 3. So when you are writing an exam, if you cannot come up with those two inequalities, you need to make sure that you ask if you can be given them, and then at least you can demonstrate that you know how to graph them and find the solution region. But to be a level 4, you would have to be able to come up with those inequalities on your own. So once you've come up with them, then it's a matter of graphing, using the test points, and seeing which region is the solution. So here is the next example. A sloop is a sailboat with two sails, a mainsail and a jib. When a sail is fully out or up, it is said to be out 100%. When the winds are high, sailors often reef or pull in the sails to be less than their full capacity. So what we have here is Jim is sailing in winds of 22 knots, so he wants no more than 80% of the mainsail out. Jim also wants more mainsail out than jib. So what possible combinations of mainsail and jib can Jim have? So what we have to do here is, again, we have to assign variables. So maybe we pick X represents the percent of mainsail that's out, and Y can represent the percent of jib that is out. Now again, we need to think here. We're thinking about percentages. What kind of values can we have? We cannot have a negative percentage, so we are definitely in the first quadrant of our Cartesian plane. But can we have partial percentages? And the answer to this is yes. This is actually continuous data because you can have parts of a percent. We could put it out 1.1% or 1.05%. So therefore, we are in the first quadrant because every value has to be positive, but we are dealing with continuous data, so we are going to be shading our regions. So now we have to look at the relationship. We want no more than 80% of the mainsail out. So that means the mainsail has to be less than or equal to 80. And it doesn't matter what it is. It can be equal, so it's got to be 80% or less. The other thing he wants is he wants more mainsail than jib. So the jib has to be less, sorry, not equals to, just less than the mainsail, because it doesn't say that they could be the same. It says he wants more mainsail than jib. So there are your two equations. Now what we want to do is, first of all, we should label this. This is the percent of the mainsail, and this is our percent of jib that is out. So now we have those two inequalities that we can look at graphing. X is less than or equal to 80. This is a vertical line. There is no Y. So what we can do is, if we go up by 10s each time, so 10, 20, 30, etc., 40, 50, 60, 70, here's our 80. So we have a vertical line at this value. Is it going to be a solid line or a dashed line? Because of that equal sign, it is going to be a solid line. So there is your percentage. So now what we have to determine, would we be shading to the left of that line or to the right of that line? It says X is less than that. So you probably could tell that we're going to shade to the left. But if you're really not sure, use your test point. So if we're putting 0 into the X, is 0 less than or equal to 80? And the answer is yes. So we need to shade in this direction. Now we look at Y less than X. If we consider this as being in the slope-intercept form, it would be Y less than X plus 0. So your intercept is at 0, and we are going up 1 and over 1. Now because we put these as tens, Up 1 over 1 is the same as going up 10 over 10. All right, 10 over 10 is 1 over 1. So we are going to be going up one space over one space. Now, because there is no equal sign, we are actually going to do a dashed line at this point. So first of all, I'm just getting my dots prepared, and then I'm going to join these with a dashed line. And because it is a dashed line, where the two lines intersect, we need to actually have an open dot, because that is not included in the solution because of the dashed line. So now what we need to determine is, are we shading above or below this blue line? So we can use our test point of 0, 0. Is 0 less than 0? What did we do? What did we forget about in this case? Because all along here we've been able to use 0, 0. The problem in this example is that 0, 0 lies on that line. So that is not actually a very good test point to use. We need to choose something else. So let's choose the test point. Again, zeros work pretty well. So why not use this point up here? It's definitely above that line, and it is at 0, 40. So the y is 40, the x is 0. Is 40 less than 0? No, it's not. It's false. So that means we do not want to shade where our test point is. So we're shading this region. And as you can see, our overlap is down in here. Remember, with the open dot at the intersection. And because it has to be in the positives, it's only above the x-axis. So now what possible combinations of mainsail and jib can we have? Well, anything that falls in this region. So let's say we chose this point here. This is at 60 and 10. So we could have 60% of mainsail and 10% of jib. Do we have to have whole number values? Absolutely not. We could have something in the middle. Maybe here we've got 45% of mainsail, and then we have 10% of jib. We could even go as far as choosing 40.5% of mainsail, figuring out, by substituting it into the inequality, we could figure out what it is in a percentage for jib. So the idea is that because it's shaded, we do not have to stick with whole numbers. We have to stick with positives, but we do not have to stick with whole numbers. So key ideas. When graphing a system of linear inequalities, the boundaries of the solution region may or may not be included, depending on the types of linear inequalities. So in the first example there, if we go back here, in this first example, we were just stippling. The overlap is not included on those two lines because the overlap of the two lines, or the intersection of the two lines, was not a whole number. But in the second example here, it is an open dot at the intersection because it is not part of the solution, because there was the one equation was not an equal to. Most systems of linear inequalities representing real-world situations are restricted to the first quadrant because the values of the variables in the system must be positive. So that's just something to keep in mind. And any point in the solution region for a system is a valid solution, but some situations may make more sense than others depending on the context of the problem. So it just might not be realistic for some of the situation or for some of the solutions in that particular situation, even though they're valid and satisfy both inequalities. So today's lesson was all about level 4, interpreting the question coming up with the two inequalities. That is definitely the hardest part. Hopefully, once you had the inequalities, you would be able then to graph them and come up with an appropriate solution.